A database transaction is the most fundamental concept behind correctness in databases. Before we talk about concurrency, isolation levels, or race conditions, we'll try and understand what exactly are database transactions. Applications rarely perform just one database operation. A transaction lets us say that these operations or these set of operations belong together and must be treated as one. Formally speaking, a database transaction is a sequence of operations that execute as a single indivisible unit. By indivisible, we mean that the database never exposes a half finished result. Either everything inside the transaction succeeds or none of it does. Every transaction follows the same life cycle. It begins with the start, executes some statements, ends in either commit or abort state. If it aborts, the database rolls it back. Taking a classic example of bank transfer, debit and credit are separate operations, but logically they form one action. Transaction exists to preserve this sort of an intent. But why are transactions really needed? Let's take an example of failure happening midway. Without a transaction, the database may persist partial work, money is deducted but never credited. This is how corruption happens. So, atomicity here ensures that there's no in between state. Either the entire transaction succeeds or the database pretends that it never happens. We're talking about the word commit here, so let's look at what does this commit mean. Commit means that all the changes that we are making are permanent. Commit is sort of like a point of no return. Once committed, changes survive any crashes and other transactions can see them. After the commit has successfully happened, the database transitions to a new valid state, and this state becomes the new source of truth. Coming to abort, abort means that the transaction cannot continue. It is a decision that the transaction has failed. Some possible causes in which this can occur include constraint violations, deadlocks, or other application or network errors of sorts. Moving on to what do we mean when we say rollback? So, from an initial original state, after some of the changes have been made but are not committed yet, internally, some changes may exist in memory or logs, but they're not visible as final results because they're not committed yet. A rollback undoes all the changes of the transaction. It is kind of a recovery mechanism. The database finally rewinds itself back to the exact state before it began. After rollback, it is as if the transaction never existed and no partial effects or like no partial transactions or changes leak out. Now that we understand what database transactions are, we can see why they matter. Transactions give us atomicity, but once multiple transactions start running at the same time, new classes of problems appear. These problems are called race conditions. In the next few videos, we'll explore different race conditions such as dirty reads, lost updates, non repeatable reads, write queues, etc. More importantly, we'll look at how databases mitigate them, for example, using isolation levels, locks, MVCC, and other transaction designs. With transactions as a foundation, we're now ready to understand like how real world databases stay correct under concurrency.